Let's talk about novae, those dazzling cosmic fireworks. A nova is like a stellar hiccup. It's bright, it's flashy, but it's not the end of a star's life. Now, don't confuse this with a supernova. Supernova are the grand finales of massive stars. They're the explosive deaths that leave behind neutron stars or black holes. Novae, on the other hand, are more like recurring light shows. They happen in binary star systems. The key difference? Supernovae destroy their parent stars. Novae don't. After a nova explosion, the star system remains intact. It's ready to put on another show in the future. Now let's zoom in on one of the key players in this cosmic drama, the red giant. These stars are in the autumn of their lives. They've burned through the hydrogen in their cores. Red giants are huge, cool, and very generous with their material. As a star becomes a red giant, it swells to hundreds of times its original size. These stars are also shedding their outer layers. In binary systems, red giants play a crucial role. They're the donors in this stellar partnership. This sets the stage for the nova show. Picture this, a bloated, elderly red giant glowing with a deep, ruddy hue, and a tiny, dense white dwarf, locked in an eternal waltz, orbiting each other in a cosmic ballet. The red giant, in its expansive phase, is losing material, shedding its outer layers into the vastness of space. The white dwarf, compact and greedy, is eager to take it, pulling in the material with its powerful gravitational force. This cosmic dance is a delicate balance, a mesmerizing interplay of forces and matter. The red giant, hundreds of times larger than its companion, dominates the visual scene. A colossal presence in the sky, the white dwarf, though small, is calling the shots, its gravity dictating the terms of their interaction. Its intense gravity is pulling material from the red giant, drawing it in like a cosmic vacuum. As they orbit each other, the red giant's outer layers stretch towards the white dwarf, creating a bridge of stellar material. This process is called mass transfer, a fundamental mechanism in the life cycle of binary star systems. It's the key to setting up the conditions for a nova explosion, a spectacular event that lights up the cosmos. Section 4. Gas transfer, a stellar buffet. Let's dive deeper into this fascinating gas transfer process that occurs in the cosmos. The transferred material forms what we call an accretion disk around the white dwarf, a structure that is both intriguing and complex. Think of this accretion disk as a cosmic whirlpool swirling with energy and matter. As material spirals in, it heats up due to friction, creating an intense and dynamic environment. This disk glows in X-rays, giving astronomers a way to detect these systems even before they go nova, providing crucial insights into stellar evolution. As the gas in the disk slowly spirals inward, it eventually reaches the white dwarf's surface, a journey that is both perilous and fascinating. The white dwarf's gravity compresses this incoming gas, exerting immense pressure. The pressure and temperature keep rising, creating conditions that are ripe for a dramatic event. And when conditions are just right, boom, we get our nova, a spectacular explosion that lights up the cosmos. Section 5, the nova explosion, a dazzling display. This cosmic event is one of the most spectacular phenomena in the universe. When enough hydrogen has accumulated on the white dwarf's surface, over time, the pressure and temperature build up. Eventually, they reach a critical point. Suddenly, nuclear fusion ignites in a dramatic burst of energy. This fusion reaction spreads rapidly across the white dwarf's surface, creating a chain reaction. The energy released is enormous, equivalent to millions of hydrogen bombs detonating simultaneously. This causes the outer layers of accumulated gas to expand violently, pushing out into the surrounding space. As this gas expands, it becomes transparent and allows the brilliant light from the fusion reactions to shine through, illuminating the cosmos. The star can become thousands or even hundreds of thousands of times brighter than it was before, outshining entire galaxies. The nova blows off the accumulated gas, but the core of the white dwarf remains intact, ready to start the process anew. After the explosion, the brightness slowly fades over weeks or months as the expanded gas dissipates into space, leaving behind a faint, ghostly glow. Ghostly. Section 6, the phoenix of the stars. Nova's repeating cycle. Here's where novae really stand out. They can happen again and again. After one nova explosion, the binary system resets itself. The red giant continues to lose mass and the white dwarf starts accumulating material again. The time between nova explosions can vary widely. It might be decades, centuries, or even millennia. This repeating nature makes novae fascinating objects of study. Astronomers can potentially observe multiple explosions from the same system over time. Each nova provides new data and insights. The study of nova ejecta, the material thrown off during the explosion, is particularly valuable.